I seem to have some problems with the stream. I hate to start it this way, so I'm going to need you guys to tell me if you can hear me properly and if you can see me properly. If not, I'm going to have to change some settings. Let's see if I can see myself properly. Okay. Something's a bit missing here. So just let me know. And then we might be able to start this. Okay. Hello, Oppie. So just to make sure, can you all hear me? Can you all see me? Because like on the Creator Studio on YouTube, it seems like it's just buffering. But it seems like if I'm looking at the live stream itself, it seems to be fine. So I'm just trying to make sure. We might change this to this. Can you explain the slope trick? I cannot understand it. It's very cool that you actually requested this. I was thinking of actually posting some educational videos as well, like tutorials on different techniques and data structures and whatnot. Unfortunately, I will not be doing it during this stream because this stream is about solving problems at first sight. So I'm considering that, and I might actually be doing that. So it's awesome that you suggested me. Everything is fine. Although my YouTube seems to be killing itself for some reason. Weird stuff. So welcome all to another live stream of me solving, or at least trying to solve, problems at first sight. For this live stream, I must say that I feel a little bit rusty. I mean, the weather is not really great and my eyes hurt a little bit, so I'm going to start off with some, actually just like my other streams, I'm going to start off with some easier problems and then we'll move on to harder problems. So let's see, there are some problems that were left in this poll, and I might also be choosing from the comment section. Okay, apparently my Gmail is notifying me that I have started the live stream. Okay, obviously. Cool. So let's see, what have we got this? Do we have some easier problems? I'm looking for now for div 2D or E problems, so this looks promising as long as it's div 2. Great Vova wall. Let's give this a little bit of a try. Oh, this is a div 3. It's actually okay. I mean, on Codeforces, in my opinion, at least div 3 and div 2 are similar in terms of the difficulty of the tasks. So I mean, d2 div 3 might be a good a good thing to start off this live stream with. So let's see what's going on. Also, if there are any problems, just let me know in the comments. I will try to look as often as possible. So trying not to mess things up because my internet has been giving me a hard time lately. Videos are buffering and I hope upload isn't going to be a problem. Also, I changed my Steam to be 180p because I know you requested it for my last live stream. That's actually why I had to postpone it with for 5 minutes, because I just realized that it might actually be better to spend 5 minutes to change the resolution of the stream, because I know you requested it. So yeah. Let's see what is going to be with this problem. Also, if you want to read the problem for yourself, try to solve it for yourself. The link is always here. So it's going to be 1092 problem D2 from Code Forces round 5 to 7. Actually, it might be a good idea to also open the easier subtask to see what the difference is. So it seems like the constraints are the same in terms of input. What's the difference? Specific to version 1, Vova can also put bricks vertically. So for version 2 cannot put bricks vertically. Okay. So height of the ith part of the wall. Okay. Okay, this paragraph tells me that it seems to be the natural way of putting bricks. Like you have 2x1 horizontal bricks that you just have to put on top of each other. So it's like just a regular wall in which you put bricks. So that's good. It seems to be pretty natural statement. All parts of the wall have the same height, and the wall has no empty spaces inside it. All parts of the wall. I see. Okay, so it seems like we are given an initial configuration of a wall. We don't have any picture, so that's a bit unfortunate. So what happens here is basically you have two, as far as I understood, you have like the map of how the wall looks in the beginning. So here would be 5. It's correcting me. It's against me. Oh god, let's put, I don't know, what other character can we put? We put comma, please. Okay, we'll put commas instead of dots because of reasons. So basically, as far as I understood, this is kind of the input, how it looks like, and you have to complete it using bricks of 2x1 bricks. For example, you can put a 2x1 brick here and raise the level, and you can put bricks here as well. So for this, I guess the answer is yes. Let's see, there are also cases where the answer is no. So how do they look? They look like 4, 5, 3. So what's happening in this 4, 5, 3 scenario? Let's see. So we have 3 here, 4 here, and 5 here. Hi, hello guys. Hello guys. Did you do a Coder Grand contest yesterday? No? Okay, sounds like something we could do. Although lately at Coder Grand contest problems, I think there's a lot of counting in them and like a lot of mathematics. At least that's how I feel about most of the late at Coder Grand contests. Maybe I'm wrong, like I haven't done this for a while. So for this, obviously the answer is no, right? Because you cannot ever put a brick there. So there's also an example where you don't have to put any bricks. So how would one approach this problem? Let's see. So yeah, one obvious thing that's just yeah, let's just say it, is that at each time you add 2 bricks, so the parity of the number of bricks wouldn't change. So no matter how many bricks you add, like if you add a brick, then the number of cells, let's say, not bricks, the number of cells just increases by 2, so the parity doesn't change. Does that tell you something? Does that tell us something useful? Well, kind of. I mean, if n is even, so if n is even, it means that the answer at the end has to be even. So if we start with odd sum, then that means it's -1. Is this the only case where it's -1? Let's see. Well, definitely not. I mean, I can see here that if we were to have something like this, there's no way that we could put a brick in this part. So yeah, I'm also wondering if the easy subtask will be helping us in some way. Just so you know, the easy subtask tells us that you can also put bricks vertically. So yeah, I mean, if you can put bricks vertically, it means that just by putting bricks vertically, you can increase any number of the input by 2. So does that help us in any way? It means that we can just raise everything to have, let's say, like you can just consider things modulo 2, so you'll have only zeros and ones, and maybe work it out from there. Interesting problem. Like one thing that you can notice here is if you are looking at the minimum value, right, it always has to have a neighbor, because like a neighbor with the same value, because if it doesn't, then you can never put a horizontal brick there. So every value has to have. So in particular, if you look at the first value, which is minimum in this array, it means that like there's no other way to complete it. I mean, you have to complete it in some way if the array isn't all equal in the beginning. So take the first value, you would have to put a horizontal brick there. And it seems like this decision is forced. So it seems to me like the algorithm that just takes the leftmost position that has the minimum value and puts a horizontal brick there and next to it, if it can. If it doesn't, it outputs -1. This algorithm is like correct in all sense. So like the algorithm is this one. Take the leftmost minimum value. If, let's say, this is position I, so position I, if I will probably want to change this. Do you guys know if I can change autocorrect on this text edit? I mean, one thing that we might do is make plain text. Like, okay, so if we make plain text, then we'll not have these problems anymore. Just tell me if you can see it properly. So position I, so if v of I equals v of I plus 1, then add, so we do v of I plus plus, v of I plus 1 plus plus. If not, we output -1, and we do this until, so repeat until all equal, of course, or it fails. So the idea is this algorithm is kind of forced. If you think about the minimum value, there's no other way that you can ever complete that brick. So if you think about, like, the minimum is basically this cell right here, right? This cell that I've highlighted. This cell, there's no way of completing it with, like, of building a solution without putting a brick like this horizontally. in this case, at least, like in the hard case. So it seems to me like this algorithm is correct, because you basically are forced to do stuff, and you're always doing something, so you always have something to do. And it seems to me that if we just come up with some sort of optimization to this algorithm to make it run faster, for example, it will just be accepted. So how to make this run faster? That's actually an interesting thing. So what are we doing here is we're incrementing consecutive values. So what will happen, I'm imagining, is like you start putting bricks, right? And you put bricks on some interval of equal blocks, and then this interval, like the minimum, will raise up to be equal to, let's say, the element to its left. So like if we have, imagine the minimum is something like this. We have bricks, and here's like empty spaces, right? And these are two walls, right? The first one can be, this is like zoomed in version, right? We're zooming in on the place where we put bricks. So we'll put bricks here, and if you look at it for a minute, you'll realize that at some point we will hit one of the walls to the left or to the right, and at that point we're basically going to have a bigger interval, right? It seems that I'm not missing anything. And yeah, how to do this? Well, let's see. What's the easiest way to do this? We're going to keep a set of intervals, right? And these intervals have a height, so we're going to keep it as we're going to decompose this picture into rectangles, basically, like rectangles that are like this. This is a rectangle, this 5 by 1, this is a rectangle, this is also a rectangle, and this is also a rectangle. And we always have to take the rectangle of minimum height and increase it until it hits one of the neighbors. Okay, and then take a different one. Okay. I guess one way to do it is with some sort of disjoint set data structure. I'm thinking whether or not it's worth it to try to do it in linear time, because maybe it might be an easier solution. But I think that that solution is also okay. So I mean, we can always also keep a set. Yeah, I think we'll go with the set, just because. So we're going to keep a set of the starting positions. Okay, yeah, we can try to code this. So first problem is going to be a.cpp, even though it's a d2. So yeah, cool. Little skeleton, we read the input. Oops, I'm for some reason declaring the vector once again. And now let's keep a set of all the positions. So let's call it, I don't know, let's actually do map of int the remaining. Okay, and for I from 0 to n, rem of I equals I. So this is like map from first to second. It's basically keeping us the pair of things that are remaining, like the left thing and the right thing. Sorry. And we'd also want to kind of put it in some sort of priority queue. So let's do we can also keep a, so we'll do queue in place back or not in place actually, because it's going to be a priority queue. Priority queue of pair. Cool. Let's call it PQ from priority queue. And what will we in place? Well, we want to process things from lesser height to bigger height. So we'll just, because priority queue is actually a max heap, we're going to be in placing minus A of I. Right. And how many times are we going to do this? Well, it seems to me that we're going to have to be doing this. Let's see. At each step, we're going to merge something with its neighbor. So how many merges? n-1. So we're trying to do n-1 iterations. Let's call it it from iteration. Okay. Let's do if minus top first is not equal to a of, actually we'll do int age and position, tie age and position equals pq top pq pop. So we've changed our minds. And if, and do age equals minus age, just to make it be good. Now, is it okay to have done this like that? Well, it seems like the first one we should be taking is the minimum one, but actually it doesn't matter that much. So you'll see. And now we have to be looking at the ranges. So also we have a position, which is the leftmost. So if position not in rem, so rem count pos equals 0, continue. And also if a of pos is not age, continue. And now we have to be looking, and this is like the leftmost part of the interval, so we'll call it L for left. Okay, so if L is not in rem, if this is not age, and we'll keep that, you'll see. And let's do R equals rem of L. This actually doesn't even have to be a map. We can just do vector of int, if I'm thinking of it right. So vector of int rem of n, and do rem of I equals I. And if rem of L is -1. So yeah. Now we have the range LR that is at height h, and we want to increase it until it hits one of our walls. So yeah, so if let's see, which way do we want to increase it? Do we want to increase it to the left or to the right? So bool to the left equals true. If L is 0, then we cannot increase to the left. Else we might want to also increase to the right if R is not n-1. So if R is less than n-1 and A of R is less than A of R, let's see, A of R plus 1 is less than A of L minus 1. To the left, false. So yeah, and if to the left, then let's call it delta, how much we're going to have to increase. So delta would be A of L minus 1 minus H. If delta greater than 0 and R minus L plus 1 is odd, we're going to have to output -1. So what have we done here? So the idea is now we have to increase. If delta is greater than, delta is greater than 0, then we actually have to increase. So in order to increase this wall, this height, we have to have this relationship. And if we have this, then we can just increase it. So how do we increase it? Well, we want to put, let's see, we want to put rem of L minus 1 equals R. Is that all? Well, AI hasn't changed, so it seems to be all. So it seems to me that we don't actually even need the priority queue. We could have just sorted it in the beginning. We'll see. Else, we also take delta equals A of R plus 1 minus H. If delta, same thing. So yeah, let's copy this. And then we'll set what? We will have to set, oh, I see. We will have to set rem of L equals R plus 1. So rem of L equals not R plus 1, but we'll have to put it rem of R plus 1. Rem of R plus 1 equals -1. And we also have to put the new thing in the queue. So PQ in place minus A of R plus 1 with L, and A of L equals A of R plus 1. And we have to re-put it in the queue. Now, is this fine? I mean, why didn't we have to put, my question is, why didn't we have to put it in this case? So I'm just trying to make sure that everything is okay. Obviously it's not okay, so we'll have to fix this. We'll have to keep like the left pointer to this and the right pointer to that. So we'll do left of I equals I and right of I equals I. Left and right, RGT of n. Okay, and this is the left. You don't actually have to care so much. So if right of L is -1, if A of L is not H, do we care? Maybe we do. So right RGT of L, and to the left. So if L is 0, to the left is false, and if A of R plus 1 is greater than A of L minus 1, we just have to make sure that also like left and right have the proper values. That's all that it matters. So that's also fine. A of L minus 1 minus H, that's fine. And we do here, what do we want to do? We want to put, so we're merging it to the left, right? So we have to put right of left of I minus 1 equals right of equals R. Is that all? Well, okay. And we also have to put A of R equals A of L minus 1. And in this case, it's A of R plus 1 minus H, and then we have to merge this into the good one. So we'll have to keep its left and modify its right. So right of L equals right of Is that fine? Right of L equals right of R plus 1. And left of R plus 1 equals L. and here right of left of that, and we also have to put left of r equals what? Left of l minus 1. Okay, and also a of l equals a of r plus 1, because that's not correct. And let's always in place, I guess, just to make sure, minus a of left of l minus 1 and left of l minus 1. So is anything going to be a problem here? Well, might be. I mean, it might be because I might be doing infinite, like an infinite loop here. So just to make sure, I'll just make sure that this is a tuple, and we'll keep the intervals I and r. Okay, if right of left is not r, or left of r is not, continue. Just to make sure, right of r plus 1. A of l here is the one that we have to modify it, and here is a of r. Seems to be it, guys. I mean, it's definitely not the easiest to implement and probably not the best solution, but it seems to be okay, I guess. Here, let's not do it like this. We'll do it while, I mean, the thing is, we're doing this n-1 iterations, and this is not correct, so we'll just do it while pq size is greater than 1. Guess that's a condition. I mean, let's do it while can pq be empty? I mean, probably not, right? Because we are always inserting stuff into the priority queue, so it can never be empty. So we'll just do while true, and here if l equals 0 and r equals n-1, we output yes, and here we output no instead of -1. See, it's good to actually read the statement. Cool. So this should be correct solution. I am not 100% sure, but I mean, damn it, might as well look at it one more time. To the left. So if L is 0, or if R is less than n-1 and R is less than l-1. Okay, to the left, and we keep delta, and we keep all of this shit. And that should be correct, right? Left of r-1 equals r, because we only care about that interval. Let's also do here, let's also do here, just to make sure, like here L disappears, so let's just do left of L equals right equals -1, and right of L equals -1. So L disappears here, and here it's who is disappearing when we're merging, it's right plus 1. So is it in the to the left? So when it's to the right, it's r plus 1 which is disappearing. So why am I doing here left of r plus 1 equals L. It should be left of right of this. Oh god, I should have, like, it would have been better if I implemented it with the DCU. I don't know why I did this. I mean, it's obviously a bad choice. And you're going to make bad choices. It depends if you want to go with bad choices until the end, and or if you want to change it in the, like, while implementing it. I decided to go to the end. Maybe it was a bad idea, but let's see. So right left of r plus 1 equals right of r plus 1 equals minus 1. And this should be correct. I mean, we've said that before, right? Oh god. Let's just compile it and run it through some tests. Okay, what have we done here? Vector. Oh, let's actually make it a little bit bigger, right? You're not going to be redefinition of R. No, we don't want to do that. Cool. So it compiled alright. Let's run it. Blah 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 something. Let's see what happened. PQ is empty. No, we messed up. Guys. Okay, let's see. So H L R. So what are we doing? We're taking 1 2 2, which is good. We're taking this one, then 1 1 2, which is good. 1 1 1, which we're probably going to be ignoring it. So let's just make sure that we did not ignore it. So did not ignore. So this one did not ignore, which makes sense. This one did not ignore. This one ignored. Okay. This one it did not ignore. And we have 203, which is good. And then we would what happened here? 203 did not ignore. And we have a -1 for some reason. So it's to the left, should be false at this point. Just a couple minutes of debugging more and it should be fine. To the left, 0, so it's going to the right. Cool. So what's happening here? A of r plus 1. Okay. Boom, and adding here a of left of L minus 1, left of L minus 1, and R. Cool. God, my leg hurts for some reason. Oh god. So 5 0 minus 1. Do we suspect anything suspicious about what we are doing? Well, it might be us setting some -1s in the wrong places. So I just want to make sure that what I'm looking at is actually correct. So 2 2, we're just adding 1 2 because it's going to the left for some reason. Okay, and Yeah, and now we're at 1, 2, and to the left, it's also going to the left, okay, and adding 2, 0, 2. Okay, so yeah, 2, 0, 3, 2, 0, okay, 0, 3, it's going to the, yeah, so basically I think we messed up here. Cool. So what did we do here? Right of L equals right of R plus 1, that should be correct. Left of right, left of that should be L. Right of L. Left of that is going to be L. Okay, I understand what's happening here. Oh god, okay. Okay, let's do int new R equals right of R plus 1. So right, we'll do left of R plus 1 equals, yeah, and this is new R, and left and new R. New R, adding A of L, L, new R. New R, and this is new R right here. See, that's why you always code stuff that you are completely comfortable with, even though it might seem overkill for this problem. Left of L minus 1. And now L is destroyed, so left of L. L is destroyed, right? Okay. New L. New L. A of R, A of new L. A of new L. New L. New L and new L. So we remove here L, and here we have to remove R plus 1. Kind of. Oh god. Right. Yes, so okay, it's working for the first, for the second it's not working, for the third, oops, for the third it seems to be working. Let's give it one more example. Let's do 5, not 5. Oh, we have to do actually 4, 5, not 5, 4, 5, not 1, 5. It's going no. So yeah, I might be comfortable doing this at this point. Like, what do you think, guys? Wrong answer on what test case? Just let me know in the comments right now. What do you think it will happen with this source code? Like, I'm not confident that this will actually get accepted, so it's also hard for me to focus with my eyes hurting. So yeah, do you think that it's going to get accepted? I certainly do not. I'm going to submit anyways, because there's like some delay between your comments and the things that I'm doing right now, so I still want to 811, so 811 is going to be the test that is going to get wrong. You say accepted. Let's see. I mean, we've worked hard at this problem. It should get accepted, right? It will probably not. Oh, damn. Wow, I have outdone myself with this thing, implementing harder solutions than the important ones. One thing that I forgot is to put these ideas here, to let these ideas be here. So I forgot to do that. Now, let's look at this solution a little bit and see like what should have been done right about it, because like I don't feel like this is the right solution to be implementing. It certainly looks like not such a bad solution, but the thing is, it's these lines that are very hard to digest, right? So it got accepted. These lines are very hard to digest. Also these things here. So it was very hard to actually reason about if it is correct or if it's not. So what I did, let's start with what I did. What I did is I took some algorithm that is supposedly forcing me to do something and just implemented it in a faster way, right? So that's basically what I did. I took an algorithm that was in complexity big O of 10 to the 9, big O of maximum coordinate, just putting one brick at a time and realizing what brick I should do, and just somehow implement it faster than just putting one brick at a time. So the idea was to kind of keep intervals of equal height, and after that just merge some intervals. Usually this kind of merging is done using something called the joint set union. I believe a lot of you should be familiar with this. I decided to go with these arrays. This is kind of a similar approach. I think what I coded here is some sort of doubly linked list, but the problem with doubly linked lists is that they're a bit hard to work with, as you have seen. Can this be done in linear time? For those of you who are really eager to figure, I think it can be done in linear time after sorting the AI array. So if you have this array sorted, I believe what will happen is this priority queue doesn't actually have to be a priority queue per se. It just it can just, I think it can be done using 2 queues. I mean, I'm not sure if it's even worth talking about it, but I think after sorting you can just keep a queue with the values, like the initial I don't know, the initial segments, which are of length 1, and kind of interleave that with the new segments that you create here. Because like, I mean, I'm not even sure, guys. But I guess if you kind of keep the interval, so here I kept the interval in the leftmost position, right? When I'm referring to an interval, like the pointer that I take to this segment is L, right? Like, but also if I were the pointer to have it to be the maximum value, one thing that could be improved here is we could keep 4 things here. I mean, it might sound overkill, but like we can keep the reference to it as being like, we can keep the interval in the highest value. So just to make sure that you understand what I mean, I'm just going to try to implement it this way. So let's see, order, we're going to put a vector pair int order. Yeah, and now we're going to sort. And my idea here is just put elements in order and keep a left, just as I've done. Keep a left and the right array, which I've populated here. So we're going to sort, and we're going to we're doing pos per second, and then we'll have to left pos and r is right pos, and from now on we can just do this thing here, which not great, but I mean something like this. So yeah, also this thing, it can be taken, and we're going to merge it into the, like we're going to keep it this way. Yeah, I guess it's going to be merged. Yeah, there's a lot of things that I've done like superfluous here. Like it can be done in this manner, and we have this delta, and now we're going to be just putting here right of L minus 1 equals R, and I think that's all. And here we're going to be putting left of R minus 1 equals L. Is that correct? I think that's actually correct, which is a bit disappointing. Like this might be actually an easier solution. So this might have been something that I should have coded, right? But I decided to code a harder solution. So let's see, a of and age. What is age? Okay, int age equals p first for whatever, or just a of pos. I think this should also be correct if it doesn't kill my program. Line 51. Left of R plus 1 here, and right of L minus 1. So this is a lot easier to code, I guess. It should also give accepted, but I didn't want to. I just wanted to make sure I write something that's correct before submitting this kind of thing, but this should also be correct. I mean, and it should work faster than 405. So 373. Yeah, the big problem about this solution is the sorting. So I'm kind of happier with this solution than with the first solution that I came up with. This is a lot cleaner. Of course, there's like you can handle this to the left easier, like, or maybe without copy and pasting code, but I'm not too bothered about that. I just wanted to show you that there's better ways to handle a problem, like to solve a problem, than just the first thing that comes into your mind. And you can think about why this is correct. I mean, it's not hard to see that it's actually doing the same thing without having to worry about data structures that are complicated to maintain, like doubly linked lists. So yeah, this was problem D2. I guess this kind of wraps it up. And I want to see, like, also D1. It seems to me like D1 is, I mean, obviously D1 is easier, right? But I think we're not going to code it. We're just going to be quickly discussing it. So my feeling about D1 is that because you can always increase every element by 2 by putting vertical bricks, then you can actually reduce this to some version of the problem where here you take it modulo 2, so you only have zeros and ones. And now if we have two consecutive zeros, then we can turn this into two consecutive ones, I mean, and damn, it actually, like, it's funny because like D1, it's supposed, usually D1s are subtasks of D2. Like if you have a problem which is noted with 1 and 2, usually the 1 is a subtask to the 2. Here it seems like there's two different problems. This one seems to be easier because probably there's some mathematics that you can prove with it. But it's funny because like solving D2 doesn't give me much insight into how to solve D1. So they're basically two different problems with a lot of the statement being shared, but they're actually two different problems. It's not one a subtask of the other. Interesting stuff. Yeah. Well, what to do? I think it's something related to parity. Like, I've seen stuff like this before, and usually what happens is you have some sort of checkerboard argument in the sense that when you put this brick, which is actually a domino, what you do is you increase the number of white cells by 1 and the number of black cells by 1 in a checkerboard pattern. So the difference between the number of white cells and the number of black cells stays the same. This is called an invariant in the general mathematical sense of it. And usually what's fun about invariance is that obviously this tells me that if the number of black cells and the number of white cells are not, like, if you look at them and they're in some way, then maybe the problem isn't solvable, and probably it's solvable in all other cases. So like it's usually that you can prove that you can solve it in all other cases. I'm wondering if this is kind of the case where it can be solved. Like one case where it cannot be solved is when n is even. Like, so it seems to me, oh, so when n is odd, it cannot be solved, because when n is odd, what's happening? 1, 2, 3. Okay, I see. So like here you have to put a vertical brick and you'll have 3, 2, 3, and here you have to put a vertical brick. It's funny. It seems to me like this is just as hard as D2. Did the standings say so? So I mean, D2 was solved by some people, D1 was solved. It seems like D1 and D2 are just as hard. It seems like there's not much difference between those. It's so funny. Okay, link the task. Yeah, sure, I can do that. So what we're discussing right now is this, and what we've discussed before is D2 problem from the same contest. So let's give it just 1 or 2 more minutes to see if we can find the solution to this problem. If not, we're going to be moving on, but probably it's going to happen. So yeah, I'm just thinking that like you can reduce it modulo 2 0 1 1 0 1, and this is okay because I see. So yeah, so it's this reduction. So I'm saying to 5, let's reduce it to 0 1 1 0 1. Now why can we reduce it like this? So basically what I'm saying is I'm going to be putting bricks such that we'll have 4 5 5 4 5, and this is just like 0 1 1 0 1 is just raising the ground level. Why is it okay to transform it like this? Basically because from this you can go to 4 5 5 4 5, which is equivalent to some extent to 0 1 1 0 1. It's just raised level, but you can also go back. So the bad thing, like a bad approach would be to say that you can reduce it like this modulo 2 and not prove that actually correct. But in order to prove it, it's just sufficient to realize that from 0, 1, 1, 0, 1, you can go to this, you can go back to this. So you can go from this one to 0, 1, 1, 0, 1, but you can also go back to it. So it's not incorrect to suppose that you've reduced the problem to this instance, because you can go back to the original instance, so you can go back and forth between the two. So that's why it's actually correct to suppose that. And in this case, basically, if you reduce it modulo 2, what happens is that the vertical brick would not change anything, and the horizontal brick would cancel out, so would toggle 2 consecutive bits. So I guess just greedy approach works, where you just take these two, toggle them to 0, and then, I mean, this is, yeah, take these two, toggle them to 0, and then take these and toggle them to 1. Roughly. So it seems to me that the only condition is that this would what? So what happens in the 1 to 3 case? In the 1 to 3 case, you have 1, 0, 1 case. So here you cannot toggle this one, right? You can never toggle this one. So like if you have a 1 with zeros on its side or a 0 with ones on its side, then it's not possible. Also another case where it's, yeah, I mean, basically I think what we can do is just like from this point just put horizontal bricks, and put horizontal bricks in the sense that if you have a 0 followed by a 1, so if we have this case, then this is not possible. And if we have, actually, yeah, you can change these two. I mean, apply maybe the algorithm of this one. Yeah, like one way of solving the one using D2 is just to do this, and yeah, and we have D1 as well, which is funny because there are people who have solved D2 but not D1. I'm not sure how to do D1 without D2. I mean, probably there is some solution that works in a binary case better. No, it doesn't want to be running. Probably wrong answer. On test 1, nice. I was quick to judge it. Okay, what happened here? To a 1 to 5, which is reduced to 0, 1, 1, 0. Oh, I see, because you in this problem you can also transforms 1 into 0, so you can also remove. So it's not just easy like this. You actually have to implement stuff. Oh well. 2 1s can turn into 2 zeros. 2 zeros can turn into 2 1s. So you can take. So what happened here is we took zeros, but we shouldn't have taken zeros. We should have taken ones. Should have taken these ones. Oh well. So not that easy. But yeah, the main idea would be that you can reduce it to this kind of problem, and this kind of problem, the way you solve it is, you know that you can basically merge an odd segment with its neighbors, and it seems that there's always a good reason to do that. I mean, you would always want to do that. So Yeah, I mean, some stack might work, I guess. It's just, oh, I think stack. Yeah, I think just stack. So yeah, I will not look. It's just like this. If size and SDK Oh God, oh God, I am making fun of myself a lot. So if SDK dot back and if that's 2, then we would want to toggle it. What's the easiest way of coding this? SDK dot back first. Size is 2 and SDK back second equals 0. We will just merge SDK back second, SDK pop back, SDK back second plus equals CNT. Something like that. SDK in place back A of I and 1. Yeah, something like that. SDK size equals 1. We'll just output yes. Else we'll just output no. Seems like it. Seems like something like that would work. Funny enough, completely different solution for a supposedly subtask. Also not an easy solution. See, it's not working. Nice, and that. Oh God, oh God, it's giving no, that's not fine. Why is it doing that? I should have always also outputted another end line. Zero, 1, okay. 0, 1, 1, 1, 0, 3, which is good. 0, 4, which is good. 0, 4, 1, 1, So the thing is, like, I haven't converted these 4s into 1s. Okay. If this, then this, continue. If we'll do int scientist back seconds, pop back second. Continue, and yeah, just break here. Should be good. Cool. Yeah, not an easy task for a div 3 at least. I mean, does this count like 2 problems? I guess it does, right? Running. Cool. Okay, well, I'm sorry I've been a little bit silent about the implementation here, but it actually what I did, which is also probably not the proper way of solving this task, is I reduced everything modulo 2. So this line is like very important. This line is essential. And the reason I discussed the reason to you earlier why we want to reduce this modulo 2. And now, in order to solve it, we just greedily merge odd like intervals with even count with their neighboring intervals. That's all that I've been doing. The thing is, like, I could have just removed even intervals, just completely removed even intervals. I'm not sure why I didn't do that. So yeah. Can you solve super egg drop problem in LeetCode? Is that some generalization about the egg drop problem? I guess. I mean, that would be... Let's actually see. Oh, do you guys have any suggestions on what I should solve next? The problem is hella boring, which is accepted of a round with subtasks. I don't think it's that boring. I mean, it kind of gave me some trouble, so it wasn't the smoothest experience, right? So to that, I just say that, hey, like, it's kind of my fault, right? If I wasn't able to very easily construct a solution for these tasks. Cool. So we're what, like 1 hour into the stream, and we've managed to solve a div 3D. That's a great day. That's a great day. 1 hour 22. Oh well. Cool. There's also beautiful mirrors maybe, but I see. I would love to suggest a problem that I have tried to read the tutorial but still don't comprehend. I'm eager to... Oh god. This is Educational Code Forces round 7, the sum of the kth powers. This seems like something that you could Google on the internet, to be precise. Like, there's some coefficients that you can find from this. It's like... So the thing is, this is always a polynomial. This is like math. I mean, it doesn't seem to me like it's programming at all, but what I would think of is, like, if you look at it, this is a polynomial of degree 2, this n times n plus 1 over 2. This is a polynomial of degree 3, which has n to the third, right? This is like the decomposition, n over 6, whatever. This is a polynomial of degree 4, and one natural thing, and actually correct for this, is to realize that 1 to the k plus 2 to the k plus n to the k is actually some polynomial of degree k in n. So that means it's some sum of ci times n to the I for I equals 0 to k minus 1. I'm sorry for this big I, because yeah, I mean, if you know how to prevent editing, what? N to the I, please. Okay, I think my machine crashed. Oh no, it didn't. It's just, oh no, prevent editing, undo. Transformation, substitution, spelling. Yeah, don't correct spelling automatically. What the hell? Why would I do that? I'm on the computer, not on the phone. Okay. So yeah, I mean, it seems like the kind of problem that you would find the solution on the internet, sum of kth powers. I mean, I'm not sure, but yeah, I will probably, yeah, this is old problem from last stream. I would probably not want to solve this problem at this particular stage, because it's heavily mathematical, it seems to me, and yeah, it's just not something I want to solve now. Problems of Kickstart round, they happen today. Is it still going? Is that still going? Oh, 68 minutes ago. This is actually div 1, problem C. Have I solved it? Make the array strictly increasing. This is like this is the classical problem. Yeah, this is the classical problem in which you can do n cubed, but you can also do n log n using slope trick. So yeah, I know this problem. Unfortunately, it's not at first sight, so I'm not going to be resolving that one. But I might try to make a tutorial on slope trick at some point. So I'm thinking of making tutorials about some different ways of visualizing some algorithms and some data structures that I think might be useful. So let's see. There's some more. Escape through leaf. I know about this problem, and please don't tell me that it's done using convex hull trick. Okay, we'll try some problem here. So it's not still going. Problems of Kickstart. Okay, I might be doing this after I pick up some problem. So probably yeah. There's a problem C suggested by me. Haha, good joke. Cut inequality down. Have we looked at it? It seems to be a problem from ICPC Latin American Regional Contest, which has been solved by how many people? Not. I've actually tried some of them. Oh, I've solved it. Yeah, I've solved it. I'm sorry. So this has to disappear from here. Okay, cool. So this one has been solved. What else? Some problem on Info Arena. I'm just going to quickly take a look at it, and then I will translate it for you guys. There's no problem. Solved by how many? Solved by quite some people. So we can actually look at it directly in English. So yeah, this for those of you who don't know, this is a Romanian online judge, which like is very popular in Romania. It's, I think, the most popular for Romanian people that are preparing for IOIs and other contests. And this is my sort of, say, platform where I sometimes post problems, and I have some I have some way of organizing it, you see. So we just copy this thing in. You can also use it. I mean, I'll probably make a separate video on showcasing it, because like it's pretty cool and I want to make it even cooler. So yeah, let's do this. Still at some point work in progress. Okay, so binary string, closed intervals of length L. Okay, so what this problem is asking us is, it's giving us a binary string consisting of digits 1 and 0, and you have to place closed intervals of length L on this string. So they have to not intersect, and they have to be inside the string and must contain at least at least a 1, right? Each of them. And you have to count the number of ways. So how to approach this kind of problem? It seems that the string is big, so the string is given that the first A1 elements are 1, the next A2 have 0, the next A3 are 1. Okay. Sorry about this. Okay. Cool. The way to solve this kind of thing, I think, length L is small. Okay, remember that even if no interval is placed, it's valid. Okay, what I'm thinking as a first thought, maybe it's not the solving thought. Let's clear this out. Is probably here is probably do inclusion exclusion. Let's move it like this. Do inclusion exclusion in the idea of, I don't know, counting everything and then subtracting the things that have an X amount of zeros. I have only like subtracted the solutions which have intervals that have zeros in them. Maybe this won't work. L is small, so the number of intervals might be big. So inclusion exclusion might be out of question here, because usually inclusion exclusion works when one dimension of your dynamic programming is the number of things that you're computing, because you, like, in order to do inclusion and exclusion, you have to somehow store some binomial coefficients. So this might be out of question. Length is small. What would happen if there were only ones in the array? Like if we only have a lot of ones. But I mean a lot of ones, potentially 1 billion of them. How would you count? How would one count this? Well, what would the dp look like? dp of n equals dp of n minus 1 plus dp of n minus l. So you either don't take it or you take it and you have l going below. So because we have this kind of formula, this tells me that it's probably using some linear recurrence ideas in this task. Because if you only have a1, like if you only have, if m equals 1, right, and you only have one thing to worry, then probably there's no other way to compute this dp apart from linear recurrence. So probably some matrix exponentiation is ahead of us. What else? How to solve zeros, obviously. Like the thing is, like if all intervals have only one, like have only values 1, then we just multiply some values given by linear recurrences. Now also if this works, like if this is of any way valuable, the number of zeros that are consecutive, they make no sense to be more than 2l. Like if they're more than 2l, then we can just consider them 2l, I guess. Is that important? I don't know. Hard to say. Okay. Cool. I think I might have an idea about this. So, first idea is reduce these values to at most 2l. So in between every two ones there will be, here it will be maximum of 60, right? And now we can do this dp. We can actually do this dp, which is just like this, but at some point there might be a lot of ones, in which case we have to fall back into the linear recurrence. Ooh, nice one. Nice one. Cool. So it's kind of a combination. It's actually an interesting problem. It's an interesting problem. If value is big, then it's dp of I minus 1 plus dp of I minus k. So it can be looked in terms of the first k elements in the one thing. So basically between fortunately this is 30, so it's a lot easier to look into. So everything here at the end, at least, it depends on a matrix and the first k elements, and that matrix is raised to some power. So what we want to do is we want to compute the matrices for the matrices that we want to multiply it for powers of 2. And then cool. Okay. So the main thing that I'm thinking about is we have this dp of n, which is dp of n minus 1 plus dp of n minus l, and this plus is optional. So this is only if there is at least 1 in dp of in there. Okay, so only if there is at least one. And now we have this dynamic, but this dynamic programming works in big O of 1 billion. So what we do, as with a lot of problems, we just take it and we optimize it. How do we optimize it? Is just that at some point, like there can be a lot of ones. If there's a lot of zeros, we can just reduce them to 60, but if to 2 times L. But if there's a lot of ones, then here is where our dynamic programming might be a problem. And the way we can sort that out is if we have a big number of ones, let's say bigger than, at some point we have bigger than 2L ones, then we can compute the last L values of the dp as depending on the first L values of the dp and some recurrence matrix raised to the power of this dp of n equals, so the dp of n minus 1, dp of n minus l is equal to some matrix m times m to the whatever, m to something, we'll see what, times dp of L, dp of L minus 1, dp of L minus 2, dp of 0. So like 0, it's in terms of the first L things. So the last L things are some matrix time to the and what power should be here? The power that should be here is actually, so if we equal n to L minus 1, so if we take the difference, we have to take the difference, n minus L minus 1, so n minus L plus 1. If we have this, then what happens if n equals L minus 1? We have this equals matrix. I think that's fine. So I think it's m to the n minus L plus 1 because it works if we equal n to L minus 1. If we equal n to L minus 1, this is m to the 0, so it will just be the initial vector. So cool stuff. Let's code it quickly and then move on to different problem. I will want to just for this, for the record, I will want to code it as fast as possible, let's say. So one way of doing that is, instead of using matrix multiplication, we can use some polynomial modulo to compute stuff like this in big O of L squared instead of L to the third. Now, the way we'll do this is using my snippet, and let's see what's happening with this snippet. We have to combine stuff. B equals combine of BB. So let's take this and let's shove it onto here. And yeah, this is basically doing linear recurrence. This is getting the kth element in time better. But if I think about it, we'll actually be getting k elements, so we don't need this. We can just use matrix multiplication. So as quickly as we manage to paste it, we're going to delete it because we're going to use matrix multiplication anyways. So what do we read? We read n and m and l, right? 4. We'll code 0, so int x sin x that's fine. V of m. So we have read our input, and that means that we have, or let's just keep it like a, like they have. We have a of 0 zeros, a of 1 ones, no, a of 0 ones, a of 1 zeros, a of 2 ones, and so on and so forth. So what we did first, we said that if I2 equals 1, a of phi mean a of phi 2 times L. And if a of phi is less than 2L, what we'll do is we'll just put, so v for j0 to ai plus plus j, we'll just put in v a of I, so I equals 0. If it's 0, then it's 1, else it's 0. Else we have to, I mean, it's obviously 1, so we're going to be putting how many ones? We're going to be putting a of I. So what we have here, we have a vector v which has values 0 and 1, and potentially some values that are bigger than 1. But the values that are bigger than 1, they're always comprised of 1s. So let's just assert that to make sure. Assert, here it should be I%2 equals 0. That's what I wanted. Assert I equals 0. I mean, it's obviously that this is how it's going to be happening. Cool. Now we have a vector v. So we can just keep the last, or not even, yeah, keep the last L rows of our dynamic programming. So to do that, we'll just take vector of int dp, which has L things, and they're all zeros, and then we do dp of, let's see, dp of 0 equals 1. And now, how do we sort this out? Just cyclically shift, I guess. That might work. Or just do dp of I. Let's just keep a dp array. And we'll keep it with skips. You'll see what I mean. Push back 0. Okay. And for all elements in V, if x equals 0, if x equals 0, we'll just keep last one pos. If x is 0, we always do dp push back, dp back, and if x equals 0, then if last one plus L. Is that correct to do? Probably yes. Okay. And we always do this. If x equals 1, last one pos kerpos. Kerpos plus 1. If x like this, then we just do brute force and we set kerpos plus equals 1, kerpos minus L here. So if it's at most 1 else then we have to do linear recurrence magic. So we have to compute the last L values given the first L values. So we just compute the first L values. So for plus I, we have a 1. Let's do int kerpos. Step, which will do this. We'll simulate the first L once, so plus last one pos, last one pos kerpos plus 1 step here. Step, and now we have the last L in our init equals init dp of end dp dot n minus L dp end. Now we have the initial and the fini, which will be compute. Now do we compute it at which power? We want n, right? We want n. So we want to compute f of n minus 1, and so on. So we said that the power that we have to raise it is n minus L plus 1. And n is the number, is x actually, in our case. Init and this. Okay, and for all auto x infini dp push back x and last one pos plus equals how many? We did L, we need x minus L. And kerpos. Was x minus L. So now we simulated x minus L steps, supposedly, So we simulated L steps, and now we need to simulate the rest of x minus L steps, and we simulate the rest of x minus L steps using exponentiation, which I haven't coded yet. Now, okay, why is it x minus L plus 1? That's what I'm a bit worried about. So we have to raise the matrix to power x minus L plus 1. Why is that so? We did L steps. Now we have to raise the power x minus L, I think. We'll see. We'll see about that. We'll see. It's easy to test. So what I'm thinking is that you just take this and then you compute it at this power. Cool. And now the recurrence is dp of n equals dp of n minus 1 plus dp of n minus L. So the matrix would have to be, so will have to be dp of n minus 1, dp of n minus L plus 1. This is matrix which has elements. So dp of n is dp of n minus 1, so 1, 0, 0, all zeros, and 1 here for n minus L, and here dp of n minus 1 is dp of n minus 1, so here 1, 0, 0, 0, oops, 0, 1, 0, 0, and 0, this is dots, right? Dots. And here would be 0, 0, 0, 1. So this is the matrix that we want to build. Okay, so we'll do vector int comp, or like we compute this matrix to the 2 to the k power. And now and after that we will just use this recurrence. So to compute this matrix to all powers, we just need 30, I guess. Vector, whatever. Void pre-compute int L. And 4. So initial matrix should be L 0. And m of 0, 0 equals m of 0, L minus 1 equals 1. And for each row, m of I minus 1 is 1. So now we've computed the matrix M, and we just have to raise it to the powers. So comp push back M for int I equals 1, I until 30, I guess. Comp push back square of comp back. And we just do vector int square m, which is just going to be multiplying m by itself. So r would be of L 0. And we're just going to be putting L to be global. Okay, and now this does m, so this returns m squared. So yeah, pretty standard stuff. Plus equals. No, this is. So this is squaring the matrix, and after that we're just going to be returning it. This seems to be good. Cool. So this squares the matrix, and then we just have to. So after we've pre-computed, we just call it pre-comp here. This does what? 30 times n to the third power times L to the third. So that's fine. Now, when we do compute of init and x minus L, we would have, so v and int exponent. So we want to compute m times exponent times v, m to the exponent times v. So we'll do for each I, if exponent has that bit, then we multiply m to the, we multiply basically what? Comp to the I times v. So we'll do v equals that. So v equals multiply comp of I v, and to vector int multiply vector int m. Here we can also put const reference and const reference here. 4. Plus 1. And in case maybe for you it might sound weird why I'm going with it like this, why I'm multiplying like this. And usually when you think of logarithmic exponentiation of matrices, you just compute m to the exponent and multiply that to the initial vector to obtain the final vector. But this is kind of an optimization, because I am doing, so I am counting this compute function multiple times. So instead of computing m to the exponent, which would take n to the third times log of exponent, I compute m to the exponent times v, which means that if I have pre-computed these matrices, this compute will be of complexity of L times third times log of exponent. So this is not L to the third. That's what I want you to see. This will be L to the second, because at each point I'm multiplying some matrix at some power with v. So I'm basically exposing the fact that if I want to compute A times B times v, where v is vector and A and B are matrices, this is A times B times v. So I'm just taking v and multiplying at a time with matrix at each power of 2. And pre-comp, this is taking O of L to the third times log of 1 in 9. So total complexity will be L to the third times log of 1 in 9 plus m times L to the second times log of 1 in 9. So it's actually an optimization. Not needed, but why not? I mean, at least if the problem is just exponentiation and some trickiness, I said that it's a good idea to show you this kind of trick. This is actually a very useful trick for reducing one for making your solution faster. And it works when you want to compute a matrix to some power times a vector, but you have multiple queries basically. So the reason why I did this is because I'm calling compute multiple times, not only once. And it's better to just keep the matrices in memory to just multiply it more easily. Well, not always, but yeah. And we'll just return res. And res will be a vector L0. And this can also be const vector of int. Okay, so we have multiplication between matrix and vector and squaring of matrix, which is all that we want. So we only want square of matrix and multiplication matrix vector multiplication. Cool. Cool. And we can also, like, if we want to be extra friendly, just do move of m, I guess. Not too important, but yeah. Square compact. Cool. Yeah, cool. Okay. So this, and here we'll just return v. That's all. That's all there is to it. Now, is that correct? I mean, one thing that we would want to test is if this is x minus l or x minus l plus 1. I'll show you a very cool way to test this very easily. For now on, let's just forget about this. So let's just do an assert false here. Okay, and do here if this thing and false, so that it will never go. Actually, I want or true. So let's just make sure that our DP works as expected before moving on. That's basically what I'm trying to do. This step. Okay, DP of 0 is 1, and here we just output dp.back. Plus this kmod. Okay. I mean, this, in theory, this should give us the right example here. You cannot push back into vector of vector, of course, because we want another vector here. Compute should not return a value. That's bad. We should want to return a value. Zero. Not great, not terrible. Because we want to push back 1 here. $55. Again, not what we expected, right? Let's first write and see. Let's output array and see what's happening here. So it's 1 1 1 0 0 1 1 0 0 0, which is good. Length L. So L is 3, and why is this giving us 55? Yeah, it's usually better to just test your stuff incrementally, especially when you're working with a problem that's in the sense of, I don't know, like IOI style or National Olympiad style. It's usually better to kind of nullify some part of the solution to just isolate the different part and just test that all in itself. So yes, what's going on here? So we have 1, and now we process this one. L is 3. So right from the start, it's something seems to be bad here. Curpos plus 1. It's actually going to be curpos, or curpos is minus 1. Oh yeah, curpos should have been minus 1 in the beginning. It's still giving me 55 though. So 1, 1, 2. Why is it giving me 2 in there? Oh, I see. Okay, so dp.back now equals now, and then we'll just push back now. This is more correct. Okay, this gives us 19, so it's good, I guess. One thing that we could do is we could try to just straight up launching it and like submitting it and see that it gives us time limit exceeded and not wrong answer. But for the purpose of this live stream, I'm going to be trying to be minimizing the number of submissions here. So I'm not going to submit it. Instead, I'm just going to try to take some case, like let's say 1.5 and put some 100, 100, 100, 3, 100 and see what's the answer on this. So it seems like what we would want to achieve is we would want to achieve 278966. Now the question is right now is if we turn off this, like if we turn back on the matrix exponentiation, if it's actually going to be helping. So if it's actually going to be doing the right stuff. Probably not. That's why we're here, because that's why I'm also like trying to implement stuff to show you what's to happen when it doesn't go right. So yeah, I'm just okay, and we just stop asserting false here. So let's note this and see. So we want for 1, 5, 1, 100, 3, 100, we would want to maybe answer is, so we're not that sure. Maybe we should have given it smaller, let's say 12, 312. Let's give it this answer because maybe this is smaller. This is actually too small. Let's do 15, 315. Actually, that might not be that bad. So 15, 315, maybe answer is 10. Okay, so let's suppose that the answer is actually 10, and let's see what our magic is doing here. And is that correct though? Because it seems to me that it cannot be correct. By outputting this dp, it seems to me that the dp values are actually decreasing, which is worrying. At least it seems to not be correct. Oh, it's because, yeah, it's because I've been I've been doing bad stuff. So and or true, we do this, and let's get the right answer. Let's also keep this. So yeah, we can see from now that our answer is bad. So maybe if I do Command Shift V or Command Option V, how can one paste without formatting? Let's do nothing here. Oops, I'm already doing bad stuff. Come on. Damn it. Damn you. Damn you, window. Okay, make this smaller and make this larger, and yeah, probably not, you're probably not going to be seeing it, but I'm going to be highlighting it, so it's fine. So for 315, our goal is to output 34 and at least some good values in the meantime. The problem is we're not doing this at this moment, so I'm wondering what might be wrong. So we cleared this. We clear this assert false, and we trying to see what's outputting. No, and 1, 5, 15, 3, 15. It's outputting 10, and some values are the same, but once it gets to the ones, it starts to be messing. It starts to be bad. 1, 1, 1, 1, 2, and then it's bad. Okay, let's do it. Let's do it. Yes. Exponent x minus l init wait, I think there's a problem here, because like I'm giving it actually, so what I'm giving it is dp of 0, dp of 1, and dp of l minus 1, and that means that I'm computing stuff in the wrong way. So just for this compute, probably what we'll have to do is we'll have to reverse and reverse here, because of the way I've written my metrics. So I could have written it in a different way. Well, yeah. Now it's giving us 34, which is alarmingly good. So this means that it seems to be correct, and the only thing that we want to do is we want to test this in different scenarios. So like maybe give it a little bit more test cases. So what we'll do is we'll just copy B to CPP to B2 to CPP. We'll edit this so that we don't do this, and we put false here. So or true, that's what we want, and clean this up and see for different values. Let's say maybe the problem was that, yeah, I've been giving it 1 instead of 3. Maybe I wanted 3, 5, 15, 3, 15. Okay, this is different. Okay, oh well, let's try it with this 3, 5, 15, 3, 15. So it's giving us the same answer, which Good, very good. Let's give it a different thing. 5, 10. That's, yeah. I think I gave it too big number. 5. Okay, this should be good. Boom. And now where to? Now it was outputting weird stuff. So yeah, let's fix this. Let's fix this real quick and just output B2. We want to output it to B2. Okay, and just what did I do? What did I 5 5? Cool. And let's just also do it with B with the same example. So it seems to be outputting more or less like from manual testing. It seems to be outputting the same things. So that's a good clue that probably the solutions are equivalent, like the linear recurrence solution with the normal solution. What we will also be doing before submitting is we'll be putting it a maximal test case. So for b.cpp, there's some stuff that I would want to comment out. Let's just comment it like this, and stuff here which, oops, stuff here that we actually don't need it. We don't need. Okay, and let's just give it the same example here, which gives 19 and also shows us that there's couts that I forgot. Okay, this gives 19. Let's give it a good strong big example, 30 30 and big. Ah, shit. Okay, let's do just I don't know, 3, and that's fine to me. And do 1. Okay, so it outputs correctly, no overflows. I think it's good to submit. So let's just okay, and we'll just submit this on Info Arena. C++, and we need live 3 b.cpp. Okay, let's see. So it's evaluating. And with some luck we got okay. So yeah, let's recap a little bit and see how we managed to AC this problem. So first of all, what I want to mention about this problem is it seems that it's kind of hard to get it right on the first try because there's a lot of stuff to worry about, right? So you kind of have to be a little bit cautious with this. In particular, what we started with is we gave it let's say a subcase of the original problem, the subcase with m equals 1 and big, like a big number of ones, and realized that in fact the key observation is that the answer follows this linear recurrence, right? So if we only give it once but a lot of ones, the answer follows a linear recurrence. That kind of gave me the idea that it's probably hard to do something better than linear recurrence. So it's probably part of the solution anyways. Like, it's a good sign that it's probably part of the solution if you don't find a better solution for this simple case, right? So after this, you kind of have to merge the idea that you might have zeros with ones with this linear recurrence, which might seem really hard in the beginning because it's hard to kind of keep track of what's like how to realize that there's a zero. There might be, I don't know, more ones. Like there's a lot of particular cases. There's a lot of cases. So what I did is I just pretended that this is the DP that I'm just computing. Like this DP is like the main thing. This is what I want to compute, but I want to compute it faster than big O of length of string, which might be up to 1 billion. So how I did this is I realized that I can skip computing some values. In particular, if there's a large sequence of ones, I can skip computing intermediate ones and just jump from these values of the DP from the first L values of the DP to the last L values of the DP by using linear recurrence. So that's the main idea. The only thing that I did is just that, and it's important to realize that that's the only thing that has been done here, because it's important to kind of keep it as simple as possible. If you complicate it, usually the more you complicate it, the harder it will be for you to solve it and to debug it. So the most simple approach that you can make for a problem is usually the best. So like the simplicity here comes, I think, from the idea of me not thinking of myself of doing anything special in particular, anything fancy in particular. I'm just taking this dynamic programming, this recurrence, and yeah, I'm just simulating the fact that, like, I want to compute it, I want to find out the millionth term of this recurrence, but I want to do it faster, just faster. But the core thing is I'm computing this dynamic programming. Yeah, just skipping some parts, in particular the big amount of ones that we have. And yeah, also there's also this thing that's optimizing us, is like if we have more than 2L zeros, we just reduce them to 2L zeros. So yeah, we have two cases basically: a case where we have a lot of ones, a lot of consecutive ones, or a case where we just have a 1 or a 0 or whatever. And in the second case, you just compute it using the last L terms of the dynamic. And in the first case, you have to compute it using linear recurrence with the first terms. Also, one very nice trick that I want to reiterate for those of you who got to the stream a little bit later is I'm not doing binary. So the idea is that we want to compute some metrics to different exponents, right? We have multiple queries of computing matrix to exponent times vector. And I did a little optimization here in the sense that I'm not computing matrix to the exponent for each query. I'm just multiplying it with matrices to different powers, to powers of 2. So it's like we're squaring, this is iterative squaring method of computing matrix to some power which is a power of 2, some exponent which is a power of 2. And we store this into memory, and when we want to compute something like matrix to the exponent times v, which is this thing here, I don't know how to, shift v, yeah, when we want to compute matrix to the exponent times v, we just take some matrix to 2 to the I for i's that are important, like for i's that respect this, right? And we multiply v with that pre-computed matrix, and this yields better complexity. This yields a total complexity of the solution, which is important. It's big O of L to the cubed times log of 1 in 9, or log of sum of values, whatever, plus O of L squared times m times log of 1 in 9. what this means is that we, like, the constraints for this problem, if you remember, are L and M up to 30. This means that we could have solved the problem even for L and M up to 100. So yeah, this solves and it can be it can be seen by the execution times here. The limit for this problem is 1 second, and we're doing it in 22 milliseconds, and probably we're fast. Yeah, we're like the fastest by a lot on the on the execution time, statistics. So we have 22 milliseconds, and then the second fastest solution is 68 milliseconds, and probably this is because this has k. This probably the rest of the solutions are something like, in terms of complexity, O of L cubed times M times log of 1 in 9. So that's, I think that's why we got off with such good times. Also, not much memory, I suppose. Yeah, but not the smallest source code. You can do smaller than that. Okay, so I hope you liked this problem. We're going to also be solving another one. I think we can do another one. So do you guys want me to solve something from a Kickstart round? Does that sound nice for you? I would like you to also... Oh, can you please have a look at Codeforces 371 problem C? So yeah, there's two ways where we can go right now. We could try a Google Kickstart question, or we could try that div1c. So just let me know in the following 2 minutes. Stop using arrow keys in Vim. Sorry about that. Unfortunately, I will never probably transition from using the arrow keys to using IJKL. Sad story. It's probably how it is. I think arrow keys are good enough. I don't think, like, there's people arguing. I mean, man, there's people arguing that using Vim, there's a lot of movement from the keyboard, from the keys to the arrow keys, and I think that's not a good enough reason for me. I don't know. You would have to be more convincing if you want me to transition from using the arrow keys to using IJKL for movement. Will I have another stream like this? Actually, I'm not sure if you're aware of this, but this is not the first stream. It shows also in the title. It's the third stream of a series of streams that are going to be just like this. So just this format, this me solving problems at first sight. This is kind of the idea around. So the answer to that question is yes, definitely. I'm going to have more like this. Probably another interesting fact is that I'm probably going to be posting videos as well, not only live streams and not only this series. I will be trying, like, if I'm going to post videos, I want them to be kind of more professional, so I'm probably going to buy a Wacom tablet or something like that to write on it. And I'm still in the process of figuring out what is the best thing to buy and what not. So what is G++11? Yes, it is an alias. I think somebody asked this question as well last stream, so I might end up putting this in the description of the video. So the the commands that I'm using, the alias that I'm using are G++11, which you can see that it's compiling with a couple of interesting things. I think the most interesting thing that you might not be aware of is this fsanitize, which allows me to trace overflows and the segmentation faults a lot easier. But this is like slow. This is really slow for testing, and for profiling and for running like actual code. I don't know, like for example, if I'm at a hash code competition and I want my code to run as fast as possible, I use G++11F, which stands for fast, which does this. I mean, I'm not even sure where I like when I wrote these aliases. They're pretty much there for as long as I have this laptop, I guess. Yes, I actually think educational videos would be great, and they will reach out to a bigger audience, because in some sense educational videos are like more to the point, and they're not as long. Like not everybody would have 3 hours available to watch a stream, but maybe they would be interested in finding out, I don't know, for example, tricks like this, how to do multiple queries of matrix exponentiation in time better than k to the third. Yeah, cool. So I'm not sure, I guess, I'm not sure what will be the next problem. So you guys seem to be suggesting me the code forces problem, because the kickstart problems are probably easier. So let's actually read at least the code forces problem, and if it's too hard or something, we'll not do it. But code forces, so the problem that we're going to be solving right now is code forces 371 problem C. So code forces 371 problem C. Maybe I've actually solved it, so it's also probably not. Is this the one? No, it's not. It should be round 371. Round 371 and any. Oh god, div1c is similar to that. 371. How to find out? Oh, it's. Oh yeah, I said. Oh, it's about this problem. The thing about this problem is, I want to make it as a separate video in case you guys want to learn kind of this technique, and also we want to solve problems that I haven't solved before, and I have solved this problem before both in n squared complexity and in n log n. So I'm sorry, it's not going to happen. So not 371c, unfortunately. There's also some problems that have remained here. We could try, I don't know, what's this one? This one is div2d. This one is a div2e, intersection of permutation. That seems interesting. I mean, we could go for this one. It's not particularly hard, but I don't feel particularly able to solve hard problems right now, mainly because I'm a bit bad at focusing. So if there was a contest today, I would probably not take it. Yeah, what do you say about this problem? Should we go for it? I mean, I'll certainly read it, so just let me know in the comments. I'll read it and then look at the comments and see if you guys are totally against it. I'm not going to be solving it, but if not, I mean, it's a div2e, so its equivalent is a div1c, supposedly, so it should be not a very easy problem. So you are given to permit. Oh, what MacBook do you have? I have a pretty recent MacBook. It's a MacBook Pro 15 inch, and it's kind of on the high end spectrum, so it's pretty good. Like I can run multiple VMs and stuff like that. It's pretty, it works pretty well. So it's not the cheapest at all. It's like a high-end configuration. Number of values which appear in both segment LARA. Oh, interesting. Okay, so we have to count the intersection and swap. So this seems to be a kind of update query problem, but the query is a little bit interesting, and the update is also like it's not a typical update query problem that you would see on judges like, I don't know, HackerRank or something like that just compute different weird aggregates. So I think it might be an interesting problem to think about, to be fair. Swap values on positions in permutation B. Okay. What I'm thinking, like the first, usually, I'm not sure if usually, but in this particular case, I'm thinking whether or not this query can actually be decomposed into easier queries. For example, if we want to calculate the number of values which appear in both that and that, we could, so let's call this ans, where is it? Okay. Let's clear this, put ideas. Let's call, so call, I don't know, call ans of L prime L prime R prime the answer to a query 1 L R L. Let's do like this. Okay, so let's call it this. I claim that ans of L R L prime R prime can be written in terms of, so write answer in terms of ans of 1 L prime. And you might be wondering, well, is this useful? How is this useful? And the answer is, I don't know, but I usually like, at least at the beginning, to try to simplify the problem as much as possible. So this is kind of a simpler query to think about than general LR, L prime, R prime. So it makes sense. It makes sense, like if you can calculate this, right? If you can calculate ans for arbitrary values, then definitely you should be able to calculate this. But the thing is, this is easier, and my claim is if you are able to calculate this, then you can also calculate the general form of the query. So how would we do that? So yeah, the thing is, if you think about one permutation, and let's put, I don't know, I should not be. So imagine I'm taking a segment of things. Let's do dots. I'm taking a segment here, right, in permutation A, and I'm taking also a segment here in permutation B. And I want to compute the number of elements that are in the intersection of this. So the thing is, because these are permutations, then elements, so what would happen if we were to calculate just this common? How many here are common? Well, part of them, like for these, for a part of them their correspondent will be here in the B, part of them will be in here. So if you want to calculate this, for example, you could imagine that you have calculated the things between the beginning of the array and this thing, and there are some elements which are here and here that you have overcounted. So you have to subtract the ones that are inside that query. So what I'm saying is, basically it will turn out that, and I'm like 99% sure, I mean, I'm kind of 100% sure, but I don't have a proper paper to put and draw these cases, but I'm sure about this, that n's of this would be n's of 1r prime, but this will overcount stuff. This will overcount n's of 1r 1l prime minus 1. This will also overcount n's of 1l prime minus 1 1r, and some things are undercounted, so we have to add n's of 1l prime minus 1 1r prime minus 1, something like this. So let's see if we can make it a little bit easier to see. So this is what I'm referring to. So I'm saying that this answer is this, so this is with plus 1r prime minus this. So it's kind of like inclusion exclusion, but it works because these are permutations. So elements that appear here only appear here. So one element appears only in one position. So that's one thing to worry. So basically what we did by this is we reduced the one queries to queries of form 1 L prime. That's all, in which we will have to compute the size of the intersection between L and L prime. Is that useful? I don't know. Let's try to go forward with this. Try to make it even simpler. What can we do? Like, how would we compute this anyways? If you think about it, permutation A will be fixed, right? So basically, so if you think about it, you can assume permutation 1 is elements 1 through n, right? Like, it doesn't matter if permutation 1 has different elements, you just reassign them to have 1 through n. And 1L prime would actually mean how many elements in this, and permutation 2 will be whatever. 1L prime would be how many elements within the first L elements are less than or equal to L prime in permutation B. That's actually the query that we're looking to solve. So how many values in prefix are less than or equal to some value, which usually is solved using, like, this is a 2D query, right? So you would want to solve it like if it was offline. In case you are wondering what I did, I checked the time limit. So if we were to solve this online, we might try sorting out the queries so that we have increasing L and keep a sorted set of R values, and in which we would just insert and try to compute how many are they with, I don't know, some Fenwick tree. The problem with this is that here we have also updates. But the good thing is, like, when you swap X and Y, it's just like erasing a value from one position and inserting a different value in that position. So it's fine. I mean, I guess what we could do is we could solve it using a 2D, any 2D query structure, like 2D segment tree, or like a Fenwick tree of sets, or a Fenwick tree of segment trees, but the segment trees have to be the segment trees they have to be they have to be sparse. I mean, it's pretty clear what I have to do now, but the thing is, like, I'm wondering what to keep as the second thing, because the problem is that as of now I am on a MacBook and there's this awesome data structure called the policy-based data structure set, which allows me to count elements, how many elements are smaller than a value, but I don't have it right now. So I'm wondering whether I should boot up a Linux machine to code it like that, or just implement it with a sparse segment tree or a trip. So trips are fun. Also segment trees. I'm not even sure what is easier at this point. Or another solution that we could do is we could pre-compute the values and use Fenwick tree on each node of the. Let's try to code it with a Fenwick tree. Just this is just like educational. It's obviously not the easiest thing that you would do, but I want to show you something. Like I want to show you that you can do this, right? So what we're going to be coding for this is we're going to be, obviously we're decomposing the queries into this form, but we're going to be keeping a segment tree in which every node is a Fenwick tree. Okay, because it is a Fenwick tree, we are allowing ourselves queries on prefix, so it's basically what we want. Okay, so we're allowing ourselves queries on prefix. So the total complexity would be log squared, and we're going to be using Fenwick tree, which means that we are going to be having a pretty easy complexity. So but the problem is that we are not able to store the whole Fenwick tree in a node of a segment tree. So what we're going to be doing is we're going to be exposing the fact that wait for it, exposing the fact that we know the values in advance to build a Fenwick tree on the compressed values. This is going to be fun. Oh god. Oh god, this is going to be fun as hell. Okay, so we are going to solve this problem offline, even though I am 100% certain, and I know that you can tell me, and I totally agree with you, this can be solved online, but we're going to be solving it offline just to show you this technique, because it might actually be a fast solution, not an easy to implement one, but a fast one. Okay, so let's read the values. We're going to be reading the permutation. Okay, and just do remap of a of I equals I. And we're going to be reading the second permutation, and Okay, we've read the second permutation, and we do minus minus a of I minus minus b of I as well, and we will do b of I equals remap of b of I. Is that fine? So we're remapping values to integers, so yeah, it should be fine. So now we're left to queries on prefix, and we only have permutation b. That's interesting. So we can actually call it v as the only thing. I usually call it v as the vector, right? This a is not useful anymore, not this remap as well. Could I zoom in a little? Certainly, thanks for telling me. Sure, I can zoom in. Is that fine? I hope it is. Cool. So we've read basically the vector initially, and now we have to read the queries. So for each query in T, we're going to be reading the type, and if type is 1, we are going to be reading L, R, L prime, and R prime. Okay, and one, and we're going to be putting it into I, whatever. I guess L R, L prime, R prime. Cool. So we have these queries, else we have an update. So we have to read XY. And it says that elements at position X and Y swap, or elements with values. Swap elements on position X and Y. So we just minus minus X minus minus Y. And then we'll do swap V of X, V of Y. And okay, so what are we going to do? We're going to be updating in the beginning at position I, right, with value I, with value V of I. And then at position X and Y, we're going to be updating with V of X and V of, at position V of X, we're going, yeah, position X. So what we'll do is we'll kind of build this kind of we have to know basically for each Fenwick tree in our segment tree which values are going to be there. So we're going to do st.fake update. This SD will be a segment tree, so we'll do, we haven't coded that yet, so just we're going to be updating at position I with value V of I. So just noticing, just telling it that it's going to be seeing V of I at X. And here we'll do st fake update at position X value V of Y, and st fake update at position Y will see V of X. Okay, and then we'll just do queries in place back to XY. Cool. Swap V of X, V of Y. And we have to also keep a backup of V, because we have to, we now have to actually do this thing. So we basically, what we did is we simulated these things without computing the actual results, because we don't know how to do them yet, but we've simulated the input, this swapping, just so that we will just so that we will have these values. So we're doing it just for these fake updates, and we need vector of tuple of int, I guess. Yeah, queries. So here will be -1 and -1 just to keep it a tuple. Cool. So now we have the queries, and now we're going to be just solving the queries. So first we initialize it. So we'll do st.init, and for each values st.update will put on position I v of I. So we're going to add 1 on position on point I and v of I. And for each query equals queries of I. So now we have each query, and if t is equal to 1, cout st.query lr lp rp. Else we'll do ct.segment3.update. Actually we can just do here int ans equals st query of l of r and r prime minus st query of l minus 1 r prime minus st query of l r and l prime minus 1 plus st query l minus 1 l prime minus 1. Cool. And we'll just see out that, and then we'll just update on. So we have x and l and r, right? This is x. So int x y equals r. We're going to be updating on x, on value v of x erase. So y v of y minus 1, swap v of x v of y, and do st update x v of x1 and st update y v of y1. So now update, what we'll do is it will add 1 on that value, and what st.query will do is it will count how many values are in that rectangular region. That's all you need to know. Okay, cool. Now let's actually do this. Okay, seg3. What do we need? We need a seg3 of n. Data will be of 4 times n, and data will be vector int. Cool. And now we have to have 3 things, right? We'll have to have void fake update init. We'll have to do update, and we'll have to do query. So there's quite some stuff that we have to implement, right? So let's get on to it. We have update, we have query, fake update, and init. So to do fake update, we'll just do fake update 1 0 n minus 1 x y. Fake update. So let's see, can we okay, what I'm thinking is if it makes sense, to have a generic function which will propagate something, but probably let's try to reuse as much code as possible. That might be interesting. Int walk Okay, and if L is XLB, R is min RE. If L greater than R, return 0. If L is B and R is E, return func, return f of node. Okay, B plus C over 2, return walk, node times 2 BMLR, F plus walk, node times 2 plus 1 M plus 1 ELRF. Cool. So now we have a function walk. What do we do with fake update? Well, we'll just do walk of 1 0 n minus 1 xx, and for function we'll just do a fake update here. So call of node push back y. So this is going to be our fake update. It will just do our thing and then return 0. Cool, because we have to return an integer because that's how we define our walk function, whatever. And we have to all. So we need all and data. Remember fake update, all that it does, so all that this fake update does is it just makes sure, it just looks at all the y values that will be present in a given node of a segment tree. So for a given node, it will just count, it will just add to its universe the y at a given x, right? So the node corresponds to some interval that contains x, and will just be given. Let me make sure that everything is okay here. It seems like it. Cool. So in each node, it's going to be making sure that it has x. So is this fine, or do we have to update it on here? It's so here is not good to walk because we want to update it in all the nodes. So that's not going to work. That's not going to work. Is it possible to make it work? Now we actually need two functions. Oh well. And this will be void. Void, not void. We'll do walk range, and this will be int walk range of r, just to keep it like that, and just we'll do walk position of pos, and this will be also void. So actually this can be just walk, and this will be like the actual query. So walk with pos. Okay, so if we'll just do f of node, int if b equals e, return int m is that, if pos walk node times 2 b m pos f, else walk node times 2 plus 1 m plus 1 e pos f. Okay, so this fake update will just put those values. So init will just be for in case you don't know what I'm doing here, is, wait, no, I cannot talk while coding this fast. So in case you don't understand what I'm doing right now, is like I want to have a Fenwick tree in each node of the segment tree, but this Fenwick tree, in order to work fast, it has to work on some compression of values. So I'm not keeping all the Y values, I'm just keeping a compressed version of it. And usually when you're compressing stuff, you're first taking note of all the values that you can have in this all array. But here I have an array for each node in our segment tree. So for each Fenwick tree, I have a node. And yeah, here I put the values, like I put all the values that I will ever need, and now I sort and unique it. This is a common pattern for normalizing stuff. Here I sort and unique, right? So this is all that it does. Now when I update, I just want to walk. I want to walk with the same helper function, and here it should be x. And at x, I have to take note of the position. So int pos equals a lower bound of all of node begin, all of node end y. I can also assert all of node pos equals y. And now I have to, so my query will be query on prefix. So it makes sense to update on suffix here. So for ++pos, this is just a regular Fenwick tree update. So I do data node pos plus equals d. Okay, so I just keep a Fenwick tree in each node, and I just add it. I add it at each corresponding node. And also here I have to do data of I resize all I size +1 0. So I have data is just going to store our Fenwick tree that is going to be keeping some on prefixes, and yeah, for all else it's just that. Cool. And now when we want to query, we would have to do query 1 0 and -1 xy, which will do our query, and this would be query. So yeah, cool. So what do we need to do here? First, this BE represent X range, right? So if P is greater than X, then we'll return 0. If E is less than or equal to X, then we need to compute the answer on the Y prefix. So we'll do some callback and we'll return ans. So and do some Fenwick tree, and in other cases we'll do query node times 2 bmxy plus query node times 2 plus 1 m plus 1 exy. Cool. This should be all. And now here, let's see, what do we need? Well, we need to compute all the values that are up to y. So you have to remap now this y to a position, into a position in the Fenwick tree. So to do that, we'll just do, let's see, we want, okay, upper bound of all of node begin, all of node end, and x, and this position will be -1, right? And just do for ++pos. Cool. that should basically be it. So we have a segment tree that's just a 2D segment tree that uses Fenwick trees as its inner, like it's a segment tree of Fenwick trees, right? And first we want to update to notify for each x the y values that are going to be in the Fenwick tree, so that we compress them, which is just doing by this. Then we initialize, right? And initialize will sort and unique all those values and assign, like allocate memory for the Fenwick trees. And when we update it, we just want to walk. At update we just want to update in the Fenwick tree, like in all nodes of the Fenwick tree. For each node in the Fenwick tree, we just assign a position and add on its suffix, just classical Fenwick tree stuff. And for query, we have a custom query walk that's just some, like if the node has value greater than x, then return 0. If it's less than x, then we have to do a query on the Fenwick tree, right? Pretty classic stuff. Cool. And that should be it. 125 lines of certainty, as a friend of mine would say. I'm just looking to see if everything is okay, and then we will try to compile. Okay, field data will be initialized, whatever. Data, go to hell. Okay. No conversion from position. Okay, upper bound, that's problematic, because we have to do minus all of node begin -1, and here I think as well. Minus all node begin. Undeclared identifier n. We need it. Do we need it? Here should be m, right? Yeah. And now we actually need it. So we just add it to the constructor list. No big deal. No magic function. No. We don't want this func to be ampersand. Control reaches end of non-void function. Line 64. Oh, I want to return this. See, always look at warnings. Like, that's a pro tip. Always look at warnings. Warnings are your friend, not your enemy. Doesn't look too great, right? Doesn't look too great. So what do we do right now? Well. Let's actually first output array v to see how it looks like. And also put this into input, because I'm going to be pasting it a lot. And I don't want to. 415236, is that good? So 5 gets mapped to 1. So this is 1. 1 gets mapped to 2. I mean, I think that's correct. I mean, it would be hard if it. I mean, I would not expect it not to be correct, I guess. 1 1. So 1 1 2 4 5. So what is 1 2? Between 1 and 2, how many elements between 1 and 2 are between 4 and 5? So the answer is 1. I'm outputting 0. Not great. Okay, so let's just do here. So by the way, most of you guys would probably just straight up write the recursive functions for segment tree. The reason I don't do that is I usually like when there's segment trees, I tend to debug a lot of stuff. So if I have these functions written and they just call a private function, as I call functions that start with lowercase character, it's easier for me to just write a CR when I need it, and you don't have a lot of bloat from, I don't know, from taking, like, from debugging inside the recursive function. Like, I don't like to debug inside the recursive function of anything. That doesn't mean that I don't, I never do that, but I like not to. So a couple more debug statements and we'll see what happens. So we do update on 0.3. So we put 0.3, 1.0. Let's just add one to each thing so that we will see it a little bit better. So put +1 here, put +1 here, and also here. Because I work 0 indexed, but I like to see things 1 indexed because I'm whatever. I'm weird. 1 4 1 2 1 1. Okay, so we added this and we have a query on 2 5. So 1 2 2 5 and 2 3. And 2 3 is giving me 1, which is correct. But 2 5 should be giving me 2. So 2 5 is giving me 1 and it should be giving me 2. Yeah, that's because I'm doing upper bound here on X instead of Y. Weird. How did that one happen? How did that one happen? Still 0, but it seems to be giving me right results. So 1 1 1 2 0. Cool. So should we submit this? I mean, why the hell not, right? Why the hell not? And if this works out as intended, hopefully after that we'll discuss a little bit what I've done in a little bit more detail. I'm not sure that it will work though. Like, I'm not 100% sure. I'm somehow sure. Intersection of permutations. Again, this could have been solved a lot easier by using the tree in PBDS, but I wanted to show you a different solution using Fenwick tree and segment tree, which might be harder, but if you are not allowed to use PBDS for some reason, or yeah, you can just wrong answer on test 3. That's always awesome. Cool stuff. Yeah, that's not great. That's not great, I must say. I wonder if this segment tree works correctly. So let's do So what I'm doing now quickly is I'm writing a brute force implementation that just simulates the 2D segment tree that I've constructed just to stress test it. Okay, so for each things, and x, y, x prime, y prime. Actually, I don't need this, right? And also this. Tuple int. Is back xyd and st fake update xy, st init for all updates, st it cool. Cool. So let's see what happens. A lot of OKs. Not great. So if there's a lot of OKs, that means that there's a high chance of me actually doing, like, me having this thing correct, like the data structure seems to be correct, which means the problem is at a different place. Let's see if, like, let's see, int a equals st query ab, oh, int r1 st query ab, r2 brute query ab. If r1 equals r2, false. test. Okay. So yeah, guys, it seems that this is all okay. Like the data structure is doing what it's supposed to be doing, or maybe it doesn't. I mean, it's hard to say. Let's do queries. Let's do n queries. Maybe it's just so many queries that, but yeah, it seems like the data structure is actually doing what it's supposed to be doing. So it seems that it is actually computing some on some on prefix and update on element. So maybe we are wrong some in a different place than the segment tree. I mean, it would be sad if this stress test would be bad and it wouldn't be doing what it, like the right thing, like it wouldn't be testing it good. I hope it does. So I hope the problem is not there. Now, what can be the problem here? Maybe this is wrong. No idea. No idea. Okay, we'll make sure to run it to make sure it doesn't fail on some test. Let's just run it a little bit. So, in case you don't know in which state we're in right now, in case you tuned in a little bit later, we are solving, or trying to solve at least, problem E from an educational round 2056. So yeah, we're trying to implement a more complicated solution to try to kind of teach you guys a way to solve 2D 2D update query problems using Fenwick tree and segment tree, and Fenwick tree that has the values compressed. What happens is, at this point, I think, like by running this stress test, it seems that the actual implementation is correct. So the implementation of the 2D update query data structure that knows how to update to add on point xy on the 2D plane a value and query on the rectangle. Unfortunately, it seems that if that is correct, it seems that there's something incorrect in the main function. So what could be incorrect here? Oh, maybe maybe it's not actually V of I. Maybe it's actually the reverse permutation which is killing. This is just... So you want to compute how many values are in permutation A. So permutation A is now 1 on n. So how many values between these between two things are in B? So okay, so this is actually problematic. So our data structure works well, but we haven't used it well. Oh God. So how many? So how, we want to compute how many values between 1 and L are in that range. So it's actually inverse to that. So you have to just V of it's sorry. How many values between? Let's keep the permutation here, like that. And we'll put at position I. Okay, and for L and R, how many values between L and R? I think this Oh god. This is so confusing. I'm sorry. How many values between L and R are inside that range? So this still follows this decomposition, but query of R and RP means how many values less than R are up to RP. So we'll just do here swap XY, and I think it should be okay. No, swap not there. So query here will be of Y and X, and it should be fine. Okay, so yeah, it was a swapping issue. God. At least the thing is, like, it was very easy to write a stress test for the data structure, so I was sure that the data structure worked well, which is very important. I mean, this gave me a lot of confidence and told me that basically the wrong thing is in the main function and not in the data structure. So let's submit it and see if it works. I would say it will probably work. Okay, so it passed test 3 and so on. So like the bug there was that I had to swap X and Y in our model because of permutations. I wonder if you guys have similar problems. I've heard a lot of people have problems when it comes to permutations because you never know if you have to be working on the permutation or the inverse of it. So have you had these kind of problems? Oh, like obviously that happened here, so I'm wondering how well it's going to be as like time-wise. But yeah, let's actually recap on it. Got accepted 5.2 seconds. That is huge. Oh god, that was huge. Why was that? That's a lot worse than expected. Am I searing stuff? Test does not get called. Weird. It's actually a lot slower than I expected. Maybe what I could have done is I could have halved the number of queries here to just do query in of R, to just query of R LP RP. This will technically half the complexity, like to make it run twice as fast. No, actually I'm messing it up again because this is Y and this is X. Confusing stuff. So this is X, so we want LP RP. Okay, minus query of L minus 1 LP RP. And here the function query will take 3 arguments. And Y. Wait, not this. Okay, let's kill the testing because we don't need it anymore. And query X will take L and R. Beam L max LB R min RE. If L greater than R, return 0. If B is L and E is R, then do this. This should technically half the number of things that we do. Maybe it will make our complexity a little bit better. But 5 seconds is a lot. I didn't expect it to be so much, and I'm not sure why it is like that. Terminate yourself. It's interesting. Oh, sync with STDO false. Thank you. Thank you, man. You might have just saved me here. Okay, yeah, probably that. Probably that as well. Let's submit this and see like the time difference, and then we'll submit it with sync STDO. Okay, let's, while it's running, let's also do this. I forgot about code forces and how important these things are with huge input. So yeah, it makes no sense at all. It's got actually bigger time, so I'm not sure what happened there. It's got 4 seconds without, which is interesting. I mean, I was hoping that this approach would be faster than any other, but it's not for some reason, and it makes me think whether or not I maybe calling this function, like outputting, like taking passing this function around, maybe that's the problem, but probably not. I mean, I'm doing this at most log n times, right? I'm constructing the function. Maybe if I do double ampersand here, maybe that will help. Let's do also sync with DO. So yeah, I'm not sure why it's working that slowly. I was expecting it to work a lot faster, but this is it. Are you going for one more problem? Probably not. I mean, my eyes hurt a lot, and I think I'll probably wrap it up here, but I want to make more live streams like this and also videos. So you're going to be hearing more from me, only not today. So, because yeah, I'm a bit tired. Maybe I got one of those viruses that they say. Hopefully not. So 4445. So it's worse if I put R value reference. Well, what can I say? I did all my best, right? Another thing. I want to if we have like a couple more minutes, I want to teach you this, like to show you this. Actually, the thing is, like, we are doing query on prefix, so let's just copy this seg tree. We can actually do something smart about it. We'll just do it in Sublime because it's easier to paste and select and whatever. Okay, so we have this segment tree. The thing is, I can actually, instead of this segment tree, I could actually use Fenwick tree, right? Like, why do I use segment tree? I don't know, because I'm an idiot. No reason whatsoever to use segment tree. So let's copy all this solution, like this whole solution. And oh, this is not the right solution. I want to copy the solution that does. So wait, it should be the solution that does more time. That was the solution. This is not the solution I want. I want my first solution. Okay, cool. Let's take this solution and optimize it. So yeah, actually it's funny because I actually have a snippet for Fenwick Tree 2D, but I didn't quite, I didn't realize basically, so I had to re-implement it from scratch. No worries, maybe it was useful for you. So what you can do here is instead of doing all of these things that I did, actually what you could do is do for plus plus x all size x all of x push back y. Done. This is fake update, right? You wouldn't need the walk anymore. Init will be for size, okay, and here data will be of size n+1, all will be of size n+1. Query is not needed anymore. So fake update will do this, and this will be Fenwick Tree 2D. So init will do this, update will do this. Right? Right. Okay, all of x and query of yx. We'll do 4 plus plus x, 4 plus plus x, x. And let's copy this thing from query and do ans here. So yeah, it's basically what I did here is I replaced my initial segment tree with a Fenwick tree because yeah, why not? I mean, it made more sense, right, to use Fenwick tree if we're doing only query prefixes. So yeah, rule of thumb, if you have reduced your problem to query prefixes, use Fenwick tree all the time, like all the way. Don't use a segment tree of Fenwick trees. Why would you do that? 11120. Let's submit this one as well. I probably also put EOS base. Boom. Let's see. Have we got any more comments? No. Okay, I'm expecting at least this. Okay, at least this gave me 2 seconds. So this is twice. This is like a lot faster than using segment tree, which makes sense, I guess, because segment tree is slower than Fenwick tree. And yeah, so this basically is 2D Fenwick tree, a Fenwick tree that allows update on point, on 2D point, and query on rectangle, on prefix rectangle. So pretty cool thing to implement, I guess. And fast, a lot faster than any other solution you would think of, like keeping sets in this Fenwick tree. So yeah, drawback is that you have to know all y values ahead of time. So you need for a given x to know all y values, like all points. You need all points that will be updated to be known before actually doing these updates. That's why I do this fake update and init. Okay, so I guess I'll wrap it up here because like I've been talking for a lot and coding for a lot with some success. I hope you enjoyed this stream. I hope you liked it. I mean, I guess it might be useful given the given the circumstances. Yeah, I guess I wish you all healthy weeks ahead of you, and see you guys next time. I guess maybe next week or in 2 more weeks. I hope it will be next week, as I am obviously, like everyone, more free in this sad period. So yeah, guys, take care, and I hope you enjoyed it, and I hope you found it educational and fun and whatnot, laughing of me. And also, if you have suggestions for what I should do next, or maybe other live streams, other formats that I should try, just let me know on Code Forces, on any of the blogs that I'm posting, even on a private message, in whichever way you feel more comfortable and you feel makes more sense, I guess. Okay, so let's wrap it up. See you guys next time.